Hi, hello everyone. Welcome to Beyond Vision to Robotics Tutorial 1 about 3D geometric basics. Let's go on to the video. In this content, you will go through coordinate frames, point, position, and translation of a 3D reference frame, and then further going to the attitude and rotation of the reference frame of robot, going with rotation matrix and representation matrix, rotation matrix and representation of the multiple rotation of the reference frames. So, have you ever wondered how a self-driving car knows where it is, or a robotic arm precisely picking an object? Well, the secret lies in the fundamental coordinate frames. So, think you are here and in the sign of robotic world, let's say you are in a point that TCF in the image, let's say you are at that point in the robotic world. So it's that way to define robot, its location and orientation in the robotic space. So today we are going to explore what these frames are, why they are so crucial, and how we gonna use them for robotic and other autonomous systems to life. Now going to the coordinate frames. Imagine your home is a world frame. So inside your home, there is a bird eye view map where you can see your living room, your kitchen, your bedroom, and your bathroom. Now the whole thing is fixed as a global reference point that never moves, and at some point you have your origin where it starts, maybe your living room or your kitchen or the corner of that whole map starts have the origin as a 3D point as 000, XYZ as a 0. Now let's say you are a robot in somewhere in the map, which is the second frame. Now you have a camera on your hand, which is the camera frame, and the image you capture is the image frame. So now you're gonna take a picture of some chair in your home. Now, how will you uh, locate the chair by using just the image to connect these all reference frame? Well, that's the idea of the robot, and that's the concept of how robots see and locate things to navigate to a object. To make simplify, you're gonna capture a image of a chair in your home, and now you get the coordinates of that pixels of the chair and convert it into the uh, camera frame as a 3D point. Now, image frame is, let's say, it's a 2D reference frame. From 2D pixels, you get it or you convert it into 3D camera points by doing some mathematical operations. From 3D camera reference frame, you convert again to robotic reference frame. Once you have the robotic reference frame, which you can convert all of them to world frame. Now on the map, you get the location of the chair where the chair is located. Once you get the location of the chair, you can navigate your robot to the chair. So this is the whole idea of how what is coordinate frame and why it's so crucial to know what is the coordinate frames. Right hand rule. So how do we orient these frames? We We use a universal convention called right hand rule. It's a simple, intuitive way to define the position and direction of the axis. Imagine your right hand thumb, your thumb points on the x direction, your index finger points on the y direction, and your middle finger points on the z direction. This is gives us a consistent way to set up every coordinate frame. By using these different frame rules, we can perform something called frame transformation. We can convert a point's location from the camera frame to the robot frame, and then from the robot frame to the world frame, as we saw in the uh, previous slide. So this magic that allows drone, let's say you have a drone and uh, this frame transformation allows your drone to spot a target with its camera and translate your transformation into its body's movement and then fly exactly to the exact location. So this adapts to drones, satellites, as well as robot. And describing the points and movements. Now that we know how to set up our coordinate frames, how do we use them to describe points and movements? So we use a powerful tool called vectors, as you would have mostly studied on your mathematics in your eighth grade, from eighth grade to high school. So this has been commonly studied by, yeah. So the powerful tool used for describing the points in the 3D is vectors. So vectors have like magnitude and direction. When we want to describe a point in a coordinate system, we use position vector. This vector starts at the origin of the frame and ends at point where we are interested in. So for example, a vector PW is the point in the world coordinate which have like three scalars, x, y, z. So these point is represented on the space which have like a vector in 3D. So now, translation of the points. So what if a robot need to move from one point to another? Use a translation vector. So one point to another. Okay. So we use a translation vector to describe this movement. So in that image, if you see P1 and P2, let's say a robot from P1 uh, moves to P2. For example, in the world coordinate system, as you can see in the image, the second coordinate system, that W, you can see in the world coordinate Cartesian system, the point P1 W moves from P1 to P2 uh, in the world system. So now, how will you find the distance? Estimate the distance between point one and point two. Well, that is being simplified by simple subtraction of the vectors. So the vector subtraction is used between point one and point two to calculate the to estimate the translation of the points. So now, point one to point one is fine, good. Now, how will you come to point two to point one? Again, it's the straightforward method which we use, inverse transform. So using the inverse transform, you will give a inverse which is P12 equal to minus P21. So you add a minus in front of the point subtraction. Now we're going to look at power of rotation. So previously we have seen the translation in 2D vectors, which applies constant for 3D also. But now we're gonna look at the rotational matrix in 2D as well as 3D. So now we have like in 2D representation, we have like x, y in the Cartesian system with origin O, and you have 2 points, which is x1, y1 and x2, y2, in which x1 and y1 is rotated with the angle of alpha to x2 and y2. Now, as you have like the right angle triangle equation, uh, we would take two triangles. We assume the two right angle triangles uh, with the 2 points, and now we compute the trigonometric identities for these two right angle triangles. So, for example, for first point x1 and y1, we compute sine mu equal to x1 by h and cos mu equal to y1 by h. So once you have this, you can transfer the h to the other side, in which you end up getting So you have like x1 equal to h sine mu and y1 equal to h cos mu. You put it into the 2D vector form, in which you end up getting x1 y1 equal to h mu cos mu h sine mu. Now same apply for the point x2 and y2, but here instead of angle to taking a separate angle, you will take alpha plus mu, angle mu. So now you have like the vector in 2D form for the angle mu and alpha. So x2 y2 equal to h cos mu plus alpha and h sine mu plus alpha. With the trigonometric identities, you will get h cos mu, uh, h cos mu cos alpha, h sine mu into and sine alpha. So going to the further step with these identities, we already know h cos mu equal to x1 and h sine mu equal to y1. So we also got that. Now going further, a we compute the we put it in the multiplicative form of the matrix. So we end up getting cos alpha minus sin alpha cos alpha multiplied by vectors of x1 and y1. So this is the rotational matrix which we need to be remembered on the further equations, further tutorials. This is the important thing that need to be uh, remembered. But going further to the 3D rotational matrix, so far we have talked about 2D matrix and 2D things. Now 3D rotational matrix is simple, as you have like three vectors combined together in the rotational matrix. So you could see there the rotational matrix W in the as referred to the world coordinate system is equal to x, y, and z world coordinate systems. As simple as straightforward. So now going to the multiple rotations, you might ask me, hey, how would I rotate from a angle on the x-axis from 30 degree and rotate to a angle on the y-axis 30 degree. So how will you reach that point? Well, so to simplify that, we use the Euler's multiple rotation theorem, and now uh, we could represent uh, the matrix of the vector in the 3 by 3 form. As you could see, the rotation around x-axis is on 3 by 3 matrix on the diagonal form. For example, on the Rx 5, it's 1 on the top, and like 0 0 and 0 cos phi minus sin phi, 0 sin phi cos phi. To for ry, it's rotational for y-axis. It's cos theta 0 sin theta 0 1 0 minus sin theta 0 cos theta. Same followed with rz. It's cos cos psi minus sin psi 0 sin psi cos psi 0 0 0 1. So this is to be remembered, and the proof will be further released on the on upcoming video. And thank you for watching. See you on next tutorial. Bye bye.